Okay, so we are going to get into our first kind of new chapter since last semester. I know chapter 6 we had covered at the very end of the fall semester with some changes, of course, with the most notable change being that kind of transition slide that went into these are all the things we did in 350 and how they're going to feed into some of the things we're doing in 351. Clearly, some things are not things you would analyze. For example, the architecture, something more of a design question. So with this first thing that we're doing, you're actually not going to be pulling in your analysis information. This is really just laying out the groundwork for the architecture that you'll be working within now moving forward. And I'll pause one more time because there's something else related to the groups that's pretty important. I'm teaching two sections of 351, and between the two sections, I think there is it's either 2 or 3 groups that are perfect matches from last semester. If you're one of those groups, the following does not apply to you. You're good to go. Just keep moving forward. If you're the vast majority of groups, which is the other 9 or 10, you do need to sort out the starting point for how you're going to move forward. And what I mean by that is, if you have, say you have a group that has 2 from Team Alpha and 2 from Team Golf, which is the analysis package that you feel would be a best foundation to move forward for design? And that's an intergroup decision. If you'd like advice from me, I will certainly talk to you and sit down and tell you which one I think you should do. But you're all adults, you're all kind of emulating the role of a systems analyst, and you have to make tough decisions like that. So you are welcome to sit down and make that decision. I said in my announcement that if you're not sure which one to use, a basic starting point could be, well, who got the highest grade? On the actual project, not individually for the entire class, but for the specific project. If one project got 95% and another project got 87%, they're both pretty good projects. I mean, it wouldn't, either one would be fine moving forward. But if you really don't know and don't have a preference, obviously you would go with the one that got the 95% as opposed to the 87%. A second step you might want to consider that's a little deeper than just who got the highest numerical grade is, say they're close. Say they're both within a few points of each other, so it's hard to really say. You might want to then look at the comments that I made and say, okay, this one, although the grades are similar, this one actually had a lot more stuff that has to be done. And this one only has a few things. So maybe we should go with the one that was closer. Even though the grades are similar for whatever reason, this one appears to be closer to what he wanted. So that could be another one. And if that's also similar, so say the grades are similar and the comments are similar, then the third option is to then just discuss it and say which one you feel has the strongest merits, or just make a decision, or come to me and say, we're really not sure which one we want. Do you have advice for us? And then I will just tell you, I think you should use X, Y, or Z. And any one of those is fine. There's not like a secret hidden agenda that I have where I'm going to secretly judge you and shake my head if you come to me. I'm really okay with that if you come and ask. Yes, Nick?
Can you reopen the sections from last semester so we can see what our grades were?
So they're not available to you? Okay. I will. To answer your question, I will. I actually wasn't sure if... It felt like Scholar got very cluttered as I was preparing for this semester, and I was trying to clean it up and just say, because the classes are named very similarly, and I'm like, it always takes me an extra little bit of time. So just to kind of clean it up, I turned them off and the little quickly links on the right. And I actually didn't know that stopped you from getting to them. I thought it was just a cleanup on my end where I wouldn't see that interface. That's terrible. You guys should be able to see all of your classes. Okay, yeah, definitely. I'll do that as soon as class is over, because otherwise I'll not remember and that'll be bad. So yeah, I'll clean that up. I would assume that a lot of you guys have some type of document management for your classes, but maybe that's not a fair assumption on my part. Like I know when I was in college, I have, and I actually still have it. I would have like a folder organization scheme where it would say like fall of say 98. I took 5 classes, and then I have a folder for each one of those classes, and then I'd have all the documents. But maybe that's not a fair assumption. So just in case you haven't done that level of anal retentive organizing that I tended to do, no expectations on my part. I'll definitely make that available for you. Yes?
I know a lot of us will have documents, but not necessarily like have every grade recorded for it.
Oh, that's true, because the way I did the grades, they're just comments. And so that's actually a really good point, because then it's unlikely you guys would have kept that. You may have the original file that you made, but then not really know for sure. You may have looked at it, but maybe not remember exactly what the comments were. So that's a really good point. For sure, I will open that for you guys. All right, and again, move on that pretty quickly, because although this first thing that we'll be doing, which actually isn't Thursday, on Thursday we're doing a casework from the text just to kind of get your feet, or your feet wet or whatever. And again, I'll be giving feedback before, so it'll be a week from today you'll be doing the first project. Even that one is not directly tied to the analysis, but I still think it'd be a good idea to have like this platform where all the team is on the same page and they know what they're doing together. Because very soon we're going to be starting to pull from that, starting to pull from the use cases, and pull from the ERD that you did, and all the stuff that you did. So it's important to all be together on that. All right, so let's go into this. So systems architecture. This used to be quite a bit more involved than it is now. There were a lot of variations. So I'm going back to like late 90s, early 2000s. There's kind of been a lot of de facto standards put in place where we've really narrowed down the scope and volume of information that you need to know, because it's very unlikely you would be outside of that scope when you're dealing with the types of system architecture that you need, particularly with the client-server architecture that is kind of just becoming the norm now in what everybody does. It's pretty rare to do a standalone application for a system-wide information system. So what we'll be doing is look at the architectural concepts, which are the ones that influence design, because understanding the architecture will inform what you need to do with your actual design for how you're going to build it. And I've made several allusions to the reality of the architecture, that kind of what you're locked into. During a lot of the interviews with the groups last semester, I kind of hinted and brought up what you'll probably be doing. So this shouldn't really be a big surprise to most of you, what you're going to end up doing. But anyway, what type of computing and software, components, protocols, interoperability, and distributed architectures. And this, in terms of your deliverable, the second point here is mostly for this stage what you'll be doing, which is to describe and draw the location, network, and deployment diagrams. This is this kind of deliverable for this particular phase, understanding how everything is laid out, essentially. Describe the system's environment by drawing architectural diagrams, entering key questions, and design larger applications based on use cases and analysis models. And again, this forms the groundwork for that. You're not actually doing that yet. This is just saying this is the thing we're going to be building on. Yes, it's important to choose the new systems, the appropriate technologies for it. But with that said, there is a reality behind this, and the first one I've already said, which is the de facto standards. So a de facto standard, if you haven't heard that term, refers to something that everybody uses because everybody uses it. I know it sounds circular, the logic sounds circular, but it is in effect what a de facto standard is. One of the best examples, which we'll get into later in this lecture, is the networking de facto standard of TCP/IP. There's no governing rule that says you have to use that, and there are other competing standards for communicating on networks, but that's what everybody uses. And if you choose to use something else, you're going to make your life a lot more difficult. If you choose to use some proprietary protocol, then you're going to have some translation software in between whatever network you're on and whatever network 99.9% of the rest of the world is on. So you have these de facto standards, number one. Number two, and the reason why I'm saying this is this word choosing. There's obviously an implication with the word choosing. Choosing means I can pick. But if I'm a little bit restricted by this de facto standard, number one, and number two, I'm restricted by what are the technologies that are already there in the organization? Because again, we're talking about organizational builds here. We're not really talking about, oh, I have a cool app idea that I'm going to make. That's a different scenario. Versus how do I manage data in a large organization? Well, that large organization is already going to have servers. And it's already going to have clients with a certain type of platform and framework that they've already invested in. So there's a monetary reality here that I have to adhere to. So I'm not sure how much choosing there really is. It's more understanding what's there. And you guys, for your project, are kind of in that boat too. It's very similar. You're not going to, all right, group, let's sit down and have a discussion for what we think is cool and what we'd like to use. No, you're kind of restricted in what you have to use, and you just have to understand that and plan for it. So yeah, we're going to describe the environment and describe the application components, all the various parts that make up systems architecture. Bless you. So right off the top, you would start thinking about the devices themselves. What devices are used in the paradigm of the systems architecture at this organization? And as I said, there already are going to be servers of some kind. Can anyone tell me, yes, it says here, manages shared resources and enables users. Other than what it says up here, if you were to describe to a layperson, what is a server? How would you describe that? And why do we have them? What's the point of a server, and how is it different from other computing devices? Any guesses? Yeah.
Kind of like a hub where everything goes to a one-stop shop.
So what's the benefit to having a hub like that for an organization?
Means everything's in one place.
So you're probably really cutting down on redundancy and duplication of data. What else? You're able to perhaps share resources. One of the major costs to a lot of organizations are licensing, and you have to pay to use software. So on one hand, if you just said everyone gets a copy of Office, and say there's 10,000 employees, a copy of Office costs around $100 for the license. How much money are you talking about here? A lot of money, $1 million, just for the licensing for Microsoft Office. Now, if you were to say, well, not everybody uses Office all the time, so if I were to have perhaps a plan for half of the organization needing this license at any given time, if I had a centralized server that could authorize the use of Office to the person using it at any given time, I've just saved the company $500,000 by sharing that resource. But the big one is centralization of data and centralization of the management of that data. So the logic around the management of that data, that needs to be centralized. So that's how I would describe a server, and I like what he said, a hub, a centralized place. I think that's a good way to, if you were to describe to a layperson, what a server is, it's a good way to think about it. On the other hand, the textbook doesn't call it this, but we have the clients. But I guess from the context of a computing device, you could just call it personal computing devices. I don't think that's necessarily a bad thing. I just like to be consistent with my nomenclature. And here we have desktops, laptops, tablets, smartphones, different devices that are used to connect to that centralized hub. And one of the major problems that a lot of organizations face today is that everyone has their own device now. And how do you treat that from a data access perspective, particularly with BYOD? So BYOD, as you probably heard, means bring your own device. So if I'm bringing my own phone to work, should I be allowed to access work-related resources with that device? And if so, how do I secure that? Most companies would like to say no. We don't want you to access those things, but the reality gets a lot murkier than that. Generally, you kind of end up facilitating it because it does increase productivity substantially to allow people to use their own devices. So here we see this basic setup of the client-server architecture where we have the servers over here. So for Amazon, you might have a payment server, a shipper server, and then Amazon itself with its own internal data sets. And you have this cloud, essentially, or labeled the internet, where different clients will access that. This is an interesting figure that the text chose because a lot of the way I've been describing this is inter-organizationally. I said, for example, 10,000 employees that are trying to get licenses is the example that I gave. And for an information systems developer, oftentimes that's how you think about things, because does Amazon have employees? Most definitely, and thousands of them. So how you think about how they access the data is how I, as a systems analyst, would be thinking about the interplay between these clients and servers. But the implication that I see here in this figure is that it's actually talking about external stakeholders. In other words, how do I, a customer, how would I interact with Amazon? There's nothing wrong with that, by the way. It's perfectly fine. It's for the exemplar, the example of all examples. I find it interesting that they chose this from a systems analyst perspective, slightly different view of how things would work, because, and this distinction that I'm making here is that there's this cloud in between the clients and the servers, which is how the customer would always interact with Amazon. But if I'm an Amazon employee, if I'm one of the, how many are there? Probably 50,000, 100,000? I'm not sure. There's a whole bunch of employees for Amazon. If I'm one of those people, I'm not on the other side of that cloud. I'm on the inside of that cloud, and there's a whole other set of things that you need to consider when they're both on the same side. For example, do I have a subnetwork where I would block off more sensitive data to data that I want, say, the people that work in shipping? Because people that work in shipping probably have different access to data than those that work in the strategy side of Amazon. It's different, and the systems architecture needs to reflect that. This somewhat simplified view is valid if you're strictly talking about customers accessing internal data. So that's the devices. So we talked about the devices, which essentially broke down to, this is, on a test, this is a pretty easy thing to consider. This breaks down to clients and servers. On the server side, the predominant platform by far would be Linux. Almost all servers are running on a Linux platform. Things have changed in the last 10, 15 years. 10 or 15 years ago, you would still have said Linux was the dominant platform, but there was a heavy presence of Windows Server. I would say back then, way back then, 2011, you would say maybe a third or so were Windows servers. It's been whittling down and down and down over the decade, where I say that I don't know for sure, and this would not be on a test, but just for your information, I would guess it's closer to 80-20 now, maybe even 85-15 for the split of Linux and Windows servers. Linux is inherently superior in every way to a Windows server. Windows servers tend to crash more. They have memory leaks. So memory leaks is where you reserve a piece of random access memory, and then when the process shuts down, you don't give it all back. It just kind of sits there taken up. So over time, you end up needing to reboot the server, which is really bad. You don't ever want to reboot a server if you can help it, because if I have a real-time server that people are expecting to access 24 hours a day all the time, and then you have this 20-minute reboot sequence, that can be a problem. So because of that, people have been slowly shifting and moving more towards Linux as a predominant platform. And I think it's a good thing. I think the reason why you have the Windows hanger-oners, it's mostly due to institutionalization. In other words, this is just the way we've always done it. This is what I'm comfortable with. What's the certification you can get? MCSE maybe. There's some Windows certification you can get that, a lot of people say, I worked for that, I have the certification, and I'm not going to support any change. This is my kingdom, and I don't support a change over to this other Linux thing. But I think over time that will continue to whittle down. On the client side, laptops and desktops, the change there that I've seen, it's still dominated. This one is dominated by Windows, actually. But there has been a slow whittling there towards Mac OS platform. And I think you could probably thank the iPhone 7, or I'm sorry, the original iPhone release in 2007. That's where the 7 was coming from. So in 2007, the iPhone came out, got people very excited about it. A lot of kids in middle school at the time that would now be, so middle school 2007 would put you, so say that's 12 years old, 1997, 1995 is when they were born, so that would put them at 25 years old now. So they're heavy in the kind of entry level area in the workforce now, and their preference, because a lot more of them percentage-wise grew up using the Mac OS and the iOS platforms. There's pressure now on the corporate side to start adopting that more and more. So there's been a slow whittling of that. On the individual user side, for sure, the numbers have changed dramatically on the individual user side. Corporate side slower, because again, there's a lot of what's called institutional inertia. In other words, the way we've always done things, and it costs money. But more and more, there's usually like a 7 to 10 year cycle for replacement of computer systems. More and more corporations are asking people now, which would you like? You can pick whatever. And if we have a standardized communications protocol, which we'll get to in a little bit here, if you have a standardized communications protocol, it doesn't really matter what platform you're on. It's not really relevant. If I'm using this TCP/IP and then I have a browser that uses HTTP, I could be on Linux, I could be on Mac OS, I could be on it's not relevant. So because of the comfort that people have, growing up with a particular platform, when given the choice, they're more likely to pick that platform than what they were annoyingly going along with, perhaps with the Windows thing when they got in. So we're seeing that start to change as well, but I'm not sure how relevant it really is. What is relevant is, of course, the network. Again, I'm ignorant with the CNU requirements, so I don't know if this is going to be vaguely interesting to you or if this is going to be below your interest level, but I don't know. Have you guys taken a networking class? Some of you? So 3 or 4 are saying yes. Oh, okay. So this will be somewhat boring, but we'll charge through it anyway. Because you've probably seen a lot of this. Obviously, you know what the definition of a network is. It's 2 or more computers linked together. You probably are aware of the major modes of that connection, whether they be physical via cables, which can be analog, such as the telephone line, or digital via Ethernet or broadband. Actually, broadband's analog as well. Or they can be radio waves with a lot of different forms, whether they be Wi-Fi, Bluetooth, cell tower, microwave. So there's a lot of different radio waves that are used for network communications, as well as optical. One of the downsides to the analog cable, of course, is that bandwidth is shared, whether it be through telephone, which I don't know if did anyone grow up at all with dial-up internet?
Yeah.
Really? Wow.
My grandparents had it.
Your grandparents? Did you ever have to suffer through using it?
Like Oregon Trail.
What'd you say?
Like Oregon Trail.
Oregon Trail. That's super old school there. Wow. Yeah, I mean, I remember the classic sound of dialing in, but and then the amazement of once we finally got broadband to say, what, I just leave it on all the time? That's crazy. I remember having to turn it off and turn the modem off, and it was this big rigmarole. But either way, if there were certain times a day that you would use your internet, broadband or not, you would see it start to slow down because you do have to share that bandwidth. Unlike optical, which you don't share it, so you don't see those variations in bandwidth that you would with the broadband. Also in terms of network topology, you probably have all seen these acronyms before: local area network, or wireless local area network is another option, wide area network, metropolitan area network, personal area network. Am I right in assuming that you guys have seen all those and know what they are? So local area network, a lot of the distinction here is just geography. It's a way to describe, now there's a lot of different ways different requirements that you have when you're implementing one of these, but the main distinction is geography. So if you were to say a test question, and I were to say something like, if you have a network that occupies a building, would that be A, a LAN, B, a WAN, C, a MAN, and so on? You should know that something that I say occupies a building would be a LAN. That would be a local area network. If I were to say you have a network that has nodes in Atlanta, Dublin, and Moscow, with the same choices, you would pick a wide area network. What about this? What's the internet of those choices? Is it a LAN, a MAN, a PAN, a WAN? I can't hear if you guys are. A PAN is personal. That's literally like on your person, like you say you connect a Bluetooth headphone to your phone, that's a personal area network, or a game controller or something, that's a personal area network. Yeah. LAN is like building size, so the internet is worldwide, right?
Oh, it would be a WAN, right?
You said with a W?
Yeah.
Yes. So that would be a WAN. That would be a wide area network. The internet is a wide area network. Trick question, is it the only wide area network? It's not really a trick question, but the answer is no. There are other networks that span very large geographies that are independent of the internet. And I'm not just talking about Internet 2, because obviously there's another large internetwork called Internet 2, but there are proprietary wide area networks as well. So large companies oftentimes have either their own communications lines or they lease communications lines that are completely cut off from the internet for security reasons. Others have what are called legacy systems. So back before we had this de facto standard with TCP/IP, everyone had their own independent protocols and communications networks, and they spent tons of money to do it. And for a while, so this would be like 90s through early 2000s, there was a debate as to whether or not the internet was something that corporations should use for communications. And the debate was, this is a public thing that everyone has access to, and yes, we can use encryption, but encryption is breakable. So should we do that, or should we stick with this thing that we've already invested in? And there was kind of back and forth for a while, until people saw it's always going to cost astronomically less to use the internet, and money talks. So they've been going away, whittling down, but they're still there. You still have some of them, and some will never go away. For example, the military has several wide area networks that are independent of the internet, as does several security agencies, not just US based, but internationally. Those will never go away. But on the corporate side, I would say at most we have about 10 more years of saying, the cost is just too different. It's about 100 times more in investment costs to have your own. So that I think that will be gone in about 10 years. So certainly know these. Again, LAN is local area network, building size. WAN is a wide area network. This would be globally. MAN is a metropolitan area network. These are generally city-sized. You might ask, where do I draw the line as a man might grow? Where do I draw the line between a man and a WAN? Generally, if you're outside the bounds of a city, you would just shift over into WAN. Hypothetically, let me give you this won't be a test question exactly, but say you saw something like this. A company has a network with nodes in Newport News, Virginia Beach, and Richmond. Which type of network is that? Yeah, because you're outside the bounds of just the city. So you would actually say, although it seems small, right? Richmond, Newport News, Virginia Beach, that doesn't really seem like a big area. It's beyond the scope of a single city. And here's a question I definitely won't ask because it's super tricky, and you could go either way with this. A company has a network with nodes in Fairfax, Annandale, and what's another city up there? I guess you could say DC. Sorry? Sure, Springfield. Technically different cities, but is it a WAN or a MAN? You could make that argument and say they're all contiguous, so it's kind of the same city, but you could also make the argument that, hey, you said, Dr. Lapke, you said that if it's outside of one city, it's a WAN, and those are all technically multiple cities. So because of that, I won't be asking that type of question. It'll be pretty clear and disparate as to the type of question I would ask for that. Looking at protocols a little bit, one of the old school ones here. Really, this is out of the text. This is why I've included it like this, because again, you guys might be studying from the text for the test, and I wanted to present it exactly the way the textbook has it. And this isn't necessarily wrong, but HTML is not a protocol. HTML is the language of a protocol, which in this case is HTTP. Hypertext Transfer Protocol is a protocol that web servers and web clients use, and that language or that protocol is communicated with the hypertext markup language. But this is how the text presents it, so I'm showing you what it says. There's also XML. This is an extension of HTML that allows you to define the semantics of tags. So the meaning, tags are how you define HTML, and it allows you to define that meaning. And then of course, there is the secure Hypertext Transfer Protocol, which essentially just adds a layer of encryption to the communications between the client and the server. Of more impact would be the TCP/IP protocols for de facto standardized networking. TCP/IP has 4 layers. At the top, this is what the user interacts with. There's the application layer that has its own set of protocols. We've already mentioned HTTP and HTTPS. These are on the website, but there are other types of application layers or application layer protocols like file transfer protocol or simple mail transfer protocol. So there are other protocols, but by bandwidth, by far, the one that's used the most, of course, is HTTP and HTTPS. Those protocols at the application layer are used the most. So the data from the application layer is then sent to the transport layer, which is where TCP resides. And you're thinking about things like error control, flow control, congestion control. And then data from that is cut into these things called packets, transport packets, which are sent to the internet layer. This is where IP is. And here we're just thinking about end-to-end communication. You're not thinking about error control or anything like that. Just get it from one point to the other. If it doesn't get there, I don't care. I'm not going to check. And then data from that is put into internet packets, and the internet packets are sent to the link layer or the data layer where the physical transmission happens, whether it be through physical cables or radio waves or whatever it is. These physical things happen at that layer. Why do we need those two in the middle? Why do we need two? Why is it TCP IP? Why isn't it just TCP or just IP? Why do you think we have two? We know what the top one, right? The top one's pretty obvious. You have to have something for the user to interact with. It has to have an application. That one makes sense. And the bottom one makes sense because we have to physically send it. And something in the middle makes sense because we have to have some type of standardized encapsulation of the data because there's going to be lots of different applications, right? So we have to have one standardized way to send it, these packets, if you will, and packets are just segments of data that are, roughly equally sized with a header on the top talking about where it's going and all that stuff. That makes sense, but why are there two? Why do you think there's two? That's definitely going to be on the test. I do ask that. I do ask why we have two. And there is a reason. It wasn't just, some of you guys might be thinking now, well, maybe it's like some type of organic growth where it just it ended up kind of like SMTP. I'm not sure if you're familiar with the email protocol, but it was written by like a teenager. And it just kind of worked, so they just kind of use it. And it's not very good, but it just kind of organically became the standard. You might be thinking maybe that's what happened here. Maybe it's just not that good, and we just kind of did it messy, and now everyone just uses it. That's not the right answer, but that might be what you were thinking. There is a specific reason why we have two. So maybe they didn't talk about that in the networking class. But let me ask this. What is the most important thing with a computer network? What are the two most important things with computer networks, do you think? Just in general, don't think about these protocols specifically, but just if I'm going to connect two things, what would be some of the most important things? Yeah. Speed, number one, I would say, is speed. Yeah. It's got to get there fast. Yeah.
Reliability.
And accuracy. You guys hit it right on the head right from the very beginning. Yeah. Speed and accuracy. Unfortunately, those are not compatible together. If I want to ensure accuracy, I'm going to have to do that at the expense of speed. If I want to have maximum speed, then I have to kind of bypass accuracy. I can't have both of those. Or can I? Well, maybe if I stack two different protocols with two different focuses, then yeah, maybe I can have both of those. If the one at the top is considered the important part for error control or accuracy, as you say, and the one at the bottom is just for end-to-end communication or speed, I might be able, I don't want to say trick the system, but I might be able to have my cake and eat it too. So what happens is, if you recall this, this slide here, we have this kind of cloud here where everything happens. So my application layer, I'm going to see that here in my, say, Chrome browser. It might be an application layer that uses HTTP. And I'm communicating over here with an Apache web server that uses HTTP. So the HTTP is going to send it through here, which is going to go through, here it's going to go through the transport layer and the internet layer. It's going to cut it into pieces. I'm going to have a transport packet, and then that's going to be put inside an internet packet, and I'm going to be sent here. Now in here, it's not a line from here to here, right? It's not one straight line where I say, okay, it's not like making a phone call. When you make a phone call, there's a direct line between you and the person on the other end. If I'm communicating between this computer right here and Amazon, do I have a direct line of communication between myself and Amazon? No, I don't. I have to go through whatever the fastest set of nodes that's going to get me there. So if you ever run a trace RT command, you can see what the various steps are for me to get there. Which, I don't know, sometimes these are blocked. Where's the search? Huh? Yeah. Oh, okay. So each of these steps are hops along the way between myself, between this computer and Amazon. I don't know what is taking so long. I lost a packet there in step 3. Huh. And so each of those IP addresses is a different geographical location that I'm going, and what they're showing here is the steps that it takes me to get from that computer to Amazon. These are all different computers that I'm hitting on the way to the... I've never seen that before. I've never seen just random timeouts going to a big server like that. I don't know. You see what's going on here. So that's representing this area. And in this area, when I'm going through each of these computers with their own IP address, I'm not going up to the transport layer. I'm only going to the internet layer in each of those nodes that I'm hitting in the internet, in the cloud. I'm only going to the internet layer. You know, it's the internet. Which means it doesn't care, and we saw some of these timeouts, it doesn't care if a packet gets from point A to point B. All it does is it comes in, and I think in a future slide I have an example of an internet header for a packet. All it says is, okay, I came from that IP address, I want to get to this IP address, I have my tables that show the ping, the amount of time it takes to get from point A to point Z, which I update all the time, and this is the fastest route, so off you go. I don't check to make sure it got there. I don't check to make sure, say there was like an NEM pulse or something on the way, say there was a power surge and some of the bits got changed and got corrupted. I don't care about any of that, because all I care about is speed. So then you might say, well then, if that's possible, how come when I log on to my bank, it doesn't just randomly say, oh, you have $1 million now because there was corrupted communications? That's because of the transport layer. At the beginning and the end, when I go back through that stack, that's when the error checking happens, and it doesn't clog up the network. So the network is just, boom, sending stuff as fast as it can. On each end, yeah, I'm doing the error checking to make sure that all the packets are correct and they got there. Does that make sense? So that's why you would have these two different protocols in the TCP/IP stack to maximize your speed, so that this is how your answer will be worded in the test question, to maximize your speed and ensure accuracy at the same time. So two disparate goals that I'm managing to meet. And here's the IP packet I was talking about. So all of the data that you put is going to be in this payload area down here, which obviously would be much, much bigger than is represented there. And then all of the metadata is going to be in the header area. Now this is an old IP version 4 header. A lot of them look different now because we're up to IP version 6, which has some additional information. But you get the idea. You know, this is the networking class. This is just showing that there is data about data, i.e. the header, that's going to be sending this information, with the most important things probably being the source IP and destination IP address, where did I come from, where am I going, the header checksum, so this is where you're checking to see if there's corruption, the length, so in case you have a different payload length, that'll help with that. So that's what we have here. And this is just another kind of representation of that thing I was talking about, where when I'm in that internet cloud, notice I'm not going above the internet layer here, and don't think that there's 2 here that it means there's always 2. If on the test, which I think maybe next week, is it next week? Is that what the schedule says? I'm following the schedule, so 2 chapters, chapters 6 and 7, if it is next week, which we'll verify before we leave today. So you'll see this question then. If I were to ask, how many nodes does a packet hit from going from point A to point B in a TCP/IP network? And the choices were 2, 5, 7, and don't know. Hopefully you would select, I don't know. Do you say 2? No, the answer is I don't know. Yeah. Because No, that's why I was specifically making that point, because some students, they think very directly, and they look at that and they say, okay, I see 2 there, and on a test, I want to make sure you don't take this too literally and think, okay, I see 2 here, that means we're going to hit 2 on the way. It's not necessarily 2. It could be 50. You have a pretty long ping time, but it could be 50. But on a test, the answer is I don't know. Well, I wonder where. So trace complete. So this one had 20. Going to Amazon. Although realistically, we could probably say 5, 6, 7, 8. We'd probably say 12, because I don't know if you really want to count these timeouts or not. Timeouts just mean I'm going to try again to get to that specific node, and for some reason it kept timing out on these. So in this case, I'd say 12 would be a more realistic number. Yeah, it looks like it's trying to take the same path again, which is pretty common, but you're not necessarily going to. You again, it depends on the degree or the amount of time it takes for a packet to go, and a router could take a different choice depending on that. But yeah, this one keeps getting those issues. Interesting. Some historical thing here. I just find this funny. The first message ever sent over the internet was actually LOL back in 1968. They didn't mean for it to be LOL, but it was. What they were trying to do is the very first network, which we'll go into the history of that a little bit as well, was I want to say Stanford to UCLA was the very first ping they sent. No, it was, did I say Stanford to UCLA? I meant the other way around. UCLA to Stanford, yeah. And what they were trying to send was a login command. And they were sending literally just the ASCII for LOGIN. But after they got to the first 2 characters, they got a dead message. As you can see in the notes here, it says dead message sent, so they have to reinitialize and try again. So then they started with the LOGIN, and they were successful the second time. But the first 3 letters ever sent on the internet ever in October 29th of 1969 was LO and then L again. So I don't, they're very stuffy scientists back then. I don't think they were trying to be funny at all. But I find it slightly amusing that was the case. So here we see the original ARPA network with 4 nodes on it. We have Santa Barbara, Los Angeles, Stanford, and University of Utah out here. And also, what's indicated in this diagram is the computer that they had. Because remember, there weren't desktops or even really servers back then. People had mainframes, and the mainframes had not only disparate platforms, they even had disparate encoding schemes. So we have kind of a de facto standard nowadays for our encoding scheme, where we always use ASCII, the American Standard for Coded Information Interchange, which ASCII uses a byte to encode all the characters that we use. But back then, they didn't have that standardized encoding scheme yet. So in other words, the very simple concept of a letter, which is our main method of communication, is the combination of letters into words and words into sentences and so on and so forth, which we then represent with bits on a computer, which we all agree now, 01000001, we all agree that that's A. You don't think like that unless you're completely weird, but all of the computers that you use do think that. But back then they didn't. And the reason why I'm making that point is that was kind of this revolution in network protocols, because despite the fact that they were disparate and they really had no way to directly communicate with each other, the fact that you're encapsulating this in these protocols and then communicating with those protocols with an application layer protocol, it didn't matter. And I kind of made that point earlier when I was talking about this slow shift towards the Mac OS in the corporate world, And I was saying, most things are communicated client-server web-based now, so it doesn't matter. It used to kind of matter. That's why everyone used Windows, and you're gonna feel sick a little bit when I say, and you were also forced to use Internet Explorer. The reason why they did that was because it did matter. But this is the first step towards it doesn't really matter, because the protocols allow you this intercommunication. And that always bothered me in Independence Day when Will Smith hooked up his MacBook to the alien computer. I was like, wait, so you're telling me they're using the same protocols that we use? There's no way. What's that? One more time so let me catch it.
No, I was like, it's still a great movie though.
Oh, it is. Oh, one of the classics of all time. I agree. But that one scene got me. And I was like, come on, dude. Yeah, I'm out of the movie now. Now I'm not really. I don't believe that there was an alien invasion. I did before, but now I don't. This is 2 years later, 1971. We see pretty slow growth. We're up to roughly 10 or 15 nodes now. We started with 4. All funded by the Advanced Research Projects Agency as a department or a subset of the Department of Defense. Why do you think they were funding this? Why was the Department of Defense funding universities to make a packet switch network?
A lot faster,
I don't know. Do you think DoD cares about that? A little bit. Yeah, efficiency's good. They certainly like that. What was the big geopolitical stuff back then? Yeah.
I mean, you could apply it in a military setting.
And why is it valuable in military setting? Well, you gotta think about what the alternative was. What did everybody use before packet switch networks?
Carrier pigeons.
After carrier pigeons, before packet switch networks. Telephone. You use telephone. Maybe telegram as well, but that uses the same network. It used the telephone network. And telephones relied on this end-to-end communication, a physical line connecting the two people talking or sending messages. The big geopolitical scare back then, 1960s, really from the early 50s through 91. What was going on early 50s through 91 geopolitically? What was the big thing? Yeah, the Cold War. This is before my time, but I remember my dad talking to me about having to hide under the desk. They did nuclear war drills where you'd actually, back in the 50s and 60s, you had to climb under the desk. People were legit scared about a nuclear exchange, and that led to a lot of the strategic thinking on the military side. And part of the thought was, if there is a nuclear strike and our communications infrastructure, say it all goes through Dallas, hypothetically, and Dallas gets taken out completely in a nuclear strike, we have no way to communicate. And they knew that would be devastating from a military strategy perspective. So their thought was, we need a decentralized network that can pick 100 different paths. So if there's a disruption in one node, it doesn't have any effect on us. That's what we'd like. And that was the request for proposal, the RFP that went out to universities where you could write grants, and they did it. But that was where the motivation came from. I find that backstory interesting when you think about why certain things happen. Why do we have this network? You think about what happened last year. Terrible events. So the Cold War was a bad thing to live through. Terrible events often lead to amazing advances. Like World War II, we had such amazing advances in technology and science after World War II. What happened last year? Coronavirus? You may have heard of it. So coronavirus happened last year. Terrible thing. It upended everything. You think any good will come from it? So germaphobes rejoice, yes.
No, not only that, but just we're gonna wash their hands more and be conscious of what they do.
Yeah.
Instead of just drinking after stuff.
Yeah, definitely. Yeah.
I actually work for a tutoring company local to where I'm from, and they were planning on pushing out an online way of instructing students,
Mhm.
but this summer, but they fast-tracked it.
Because of
Yeah, and
coronavirus.
also it's, at least for right now, I've been allowed to still work here for the school because they're like, well, we can't bring new instructors in like we intended, so I guess it doesn't matter.
So for you, it's win-win.
Yeah, and even
Yeah.
moving on into the future, they get so much good experience of instructing online, just as a training, but also from a network perspective, using the website they're using and all that.
Mhm.
For when they can finally do what they intend to do, that was just to change the background to the online instruction.
Right, and I mean, there's a lot of benefits to that for sure. Yeah. Yeah.
A lot of companies are realizing that their employees actually really like working from home.
I was gonna say,
And
work from
also
home.
going-
Yep. Yeah, there's a huge, although there's this weird management perspective that if I'm not looking at you, you're doing something wrong. So I think you're right, we'll see a shift, but I don't think nearly as much as it could. I think it could go a lot more. My brother-in-law, he almost died in 2017. It's actually why I live here now. Because my wife and I were like, we're not happy here, and because it kind of changes. He did survive. He had what's called a widowmaker heart attack. This is the one where the main artery that comes down your heart gets blocked, and it kills you like 90-something% of the time. He happened to be in the emergency room because he just felt off. He was at work, and then for lunch he's like, I don't know, something's not right, and he died right there. He just heart stopped. They did the resuscitation. He's in a coma for like 2 months, but now he's fine and everything's good. So he's pretty high risk being in that scenario, and he loves working from home. He absolutely loves it. And initially they were like, well, we'll allow 25% of our employees to stay working from home. And then as we all just kind of got used to this virus, we're gonna make that 0% now. So he was like begging and pleading, like, please, I really want to stay home. I really want to stay home. And they just, but that's just that company, you know. It's not all. I think you're right. I think we see a shift, but not as much as we could. Particularly knowledge jobs. Like most of you guys are going to end up in knowledge jobs. You might be a cybersecurity person. You might be a systems analyst. You might be a developer. You might be things that you're using your brain to do your job. I think all of you could work from home should you choose to. But I think you'll see maybe not as many of you as that would hope. Did you have one too?
I was gonna say, I feel like there's a lot of time people just like go to work sick, or like little like.
Oh yeah, and that's not acceptable anymore.
Yeah.
Yeah, and I think there is some more understanding with that too. Again, the Dilbert comic strip is depressingly accurate, whereas managers are idiots, and I think we'll slowly shift that back to, I expect you to come in either way. Hopefully not. But actually, what I was thinking, you guys are all great ideas and thoughts, but I was actually thinking the medical advancements that are going to occur because of this. I would say by 2025, we'll see many new cures for cancer. They're already talking with the mRNA. They actually have vaccines for melanoma, breast cancer, pancreatic cancer. What else? What's the other ones that I heard? Because it's a very similar technique that they use, and this kind of sped up the whole mRNA vaccination thing. But there's a husband and wife that formed a company in Germany, the BioNTech, that works with Pfizer. They started it to cure cancer. And now they say, now that we've had this data, we think we can actually get there. We can do this now. Multiple sclerosis, Alzheimer's, these all may be things of the past thanks to coronavirus in a way. It's weird to say that, but that we could see really a burgeoning, not to mention all the societal stuff that you guys said. You know, we talked about being clean, working from home, all this stuff you guys were saying. There could be something good that comes out of it. So let's be optimists here while we can. All right. So we had this this slow growth. We were four nodes. A couple years later, we're up to like 10. Here we are about coming up on 10 years later, where for the ARPANET has roughly 25 or 30 nodes at this point. So pretty slow linear growth, and the reason why is because it was government funded, and I have fought for grants before, and it's like pulling teeth to get grants even for really good ideas. And these people probably ran into some of the same issues. You start to see, if you look closely at this, you start to see it's primarily universities, but also government laboratories and military as well are starting to get involved at this point in 1977. You also are starting to see it's not just one computer that organizations have, now they have 5. So you're starting to see the growth in that as well, more investment in technology. A more recent picture, there's billions of nodes here, of course. But when did we turn from linear to logarithmic growth, and why? So linear was government funded, right? Yeah.
When it went more public.
Yeah.
People became more interested, and the money that they were got, people were interested.
Yeah, I graduated college during the dot-com boom. And I lived through this explosion right in the middle of it. It was utterly insane. I can't explain how crazy it was. I had friends that dropped out of college to form companies and were immediately given venture capital in the millions of dollars. I'm talking about history majors. I'm not saying people with me in computer science program. I'm saying history majors that didn't even know how to program, but they made an LLC, which cost like $50 to make an LLC, with the word web in it. And they were given millions of dollars in venture capital. It was insane. And this isn't Jacksonville. This isn't Florida. This isn't even, Silicon Valley or somewhere where you'd expect it. This is the middle of nowhere, from the technical world. So crazy time to be around. Private companies saw a way to make money, lots of investment, lots of growth is where that happened. All right, moving on from network into software. I have talked about a lot of this already. Application software, these can be custom apps that are built specifically for the organization. We're starting to see this less and less just because of the time commitment, and the failure rates tend to be a little bit higher, but it is still a possibility that you can make custom software on the application end. More and more, you see that sub-bullet points there says web-based applications. More and more we're starting to see just strictly going on the web or mobile side. System software, this is behind the scenes, and I've also alluded to this as well. So this is kind of the foundation for which everything else you can work on. And when you think about, computer science versus information science or information systems, how would you make that distinction? If someone were to ask you, say you're hanging out with people at a party and they're like, so what's your major? And you say, I'm information science. Oh, that's like computer science then, right? Well, how would you respond to that? In a way they could understand, not, well, actually, I only take CPSC up to 250. I don't take 270 and 350. They don't know what any of that means. How could you say it in a way that, you're making conversation, you're not talking about Kansas City and, Super Bowl coming up. You're talking about real fun stuff, classes. Yeah.
Just say you kind of dabble in it a little bit, but don't take higher level classes.
See, that's talking down on yourself. You can't.
Or you could say like, oh, I know how to program in like these languages, or like I know how to program in these languages, not like elaborate.
Okay, so that could be like an applied description as to how it's different. Yeah.
I would just say it's kind of like on-site and more like business integration.
I like that. That's a good way to describe it. Let me give you the best way to describe it. Because you're throwing a little bit of shade at the CS people, and for those CS people in here, I'll apologize ahead of time. Please don't say you hate me. Student evaluation things. Here's how you could say it. And this is true, by the way. This is not false. This is exactly the distinction that is between CS and IS. CS people are trained to build system software. System software. They're trained to build, what is system software? The big one you look at are operating systems. That's the main one. That's the platform that everything you do on is on the operating system. They're trained to think about that. High levels of optimization, high levels of efficiency, memory management, user interface. They're really down in that. Really, the user interface, I'm going to say no. I'll take that away and not even include that in the operating system. The most important thing is the kernel, the behind-the-scenes stuff. What about a platform for building, also known as compilers? Computer science people are trained for that. What about how a DBMS is actually built itself? Not using the DBMS, but building the DBMS. Computer science people are good for that. Now, okay, so then that's fine. But what about the people that actually build the applications that are used? That's what IS people are trained to do. They make use of that infrastructure that CS people make available to them. Now, does this mean a CS person isn't capable of building a user end application? Certainly not. They definitely have the skills to do that, without a doubt. But that's not what they're specifically trained for. They're specifically trained for the system side. For the application side, so you could say, that's a long description, but if you're at a party and you're having a pithy back and forth, you could say, I make the software that people use. Computer science people, they enable me to do that. That's a short and pithy way to describe the difference between CS and IS. Now, I liked what he said about having a deeper understanding of the business requirements and all that. I mean, that's certainly important because there is more of a business focus on the IS side, but that's a whole discussion. Just a short discussion is system versus application. That's the short discussion. Yeah.
Like how the theoretical mathematicians provide the applied mathematicians with
Yeah.
tools they need to develop their models. and
Yeah,
stuff.
exactly. And, you know, the applied mathematician's job would be infinitely harder without those theoretical people giving them that foundation. So, yeah, very good. And here we see the same thing that we saw on an earlier slide where you have the operating systems, web servers, application programs, and DBMSs here on the server side, and operating systems, web browsers, and apps on the client side. So the web-based applications, this is what we see more and more. Obviously, it's required that you use a web browser. Generally, there aren't any restrictions, which for a developer, and in this case an IS developer, actually is a big pain. Because the reason why I say that it's a pain that there's no restrictions is because now you're responsible for developing for every possible use. Do you think the code for Chrome, the HTML and XML and CSS and all that code for Chrome is exactly the same? Is it going to look exactly the same on Firefox? Look exactly the same on Safari? No, there's going to be definite differences, and you have to have essentially a big conditional, a big if statement at the top that says, what are you using? Oh, you're using Firefox? Here's the code for that. So it kind of triples and quadruples the amount of code you have to write. To test for all of those things. It's the bane of the web developer's existence is that. Obviously access through URL, resides on a web server, yes, all of this stuff. And then of course we have the embedded as well. I don't know how we ran out of time, but We'll go as far as I can go, and then what we'll do on Thursday is I'll touch base on the really important thing, if I don't get to it, which I don't think I will, that you'll have to do for your in-class assignment. So there'll probably be a short 10-minute continuation of the lecture on Thursday before you start the group work, because I don't think there's no way I'll be able to get to this. So we talked about the technology architecture as well as the application as well. This would be on the software side. We've already talked about web services. Software function that's executed with web standards, again through the URL remotely. And I've also briefly addressed not briefly, actually the whole conversation has been intertwined with the client-server architecture where your client, which would be your basic computer, sends a request through the cloud essentially, which would then connect to a server and it would respond as needed. And oftentimes there's going to be a 3-layer architecture, which we have for your project in this class. It will be a 3-layer architecture. Again, I advise you guys, we're not going to use Amazon Web Services. We're going to use the local option instead, and you'll be downloading MAMP. And right in the title, you have your layers. So you have the client, which you're going to use to access it, and then it's going to be accessing tightly connected to the server, which is the A part, or Apache. That's one layer, which will then communicate through a server-side script. That's the P, that's PHP, that's the second layer. And then the third layer is the other M, which is MySQL, that's where the data is stored. So right off the top, you guys are going to be working in a 3-layer architecture. All right, that's it. We are out of time. So what I'll do on Thursday will be definitely these 3 slides I'll have to go through in pretty close detail, because this is what you'll be using for your casework project for that day. I'll see you guys in class on Thursday.